And so, in a lot of books, this would be the beginning of a new chapter, and then the previous chapter would have been on electromagnetic waves. And then we would have a separate chapter on geometric optics or ray optics. I'm going to start off with a discussion about wave fronts and rays. And so this is the beginning of geometric or ray optics. And so when we talk about a wave front, then what we get is that a wave front is a surface constant phase. And so what that means is we'd go in and look at, all the peaks, or we could do all the troughs. I mean, you can do any other point, but usually it's peaks or troughs kind of things. And I usually picture just the all peaks. And when we talk about a ray, so a ray is an imaginary line that runs perpendicular to the wavefronts. And in the direction of propagation. Or the direction in which the energy is being transported. Of the wave. And again, keep in mind that a wave, what a wave does is it transports energy. Okay. And so when we go into have our, this discussion, then what I want you to do is I want you to consider that we're going to go in and drop a pebble into a pond. And the reason for a pond is I want that the surface of the water to be pretty smooth. And so then what we're going to do is we're going to watch that the ripples that are created by the pebble striking the water are going to travel outward from the location where the pebble hit. Okay. And so hopefully you can kind of picture that. And then what we're going to get is that, the pebble's going to hit at one point, and then we're going to generate these ripples. And the thing about the ripples is that they're going to make these kind of concentric circles or rings. And so we'll say that the pebble hits here at the center. And so what this is going to act as is it's going to act as kind of a point source of our waves. And then what we're going to look at, so this is the act as some sort of point source for our waves. And then if we go in and take a look at measuring the distance away from that point, we'll mark this as R. It's like some sort of radial distance from the point where the pebble hits. Then we can go in and we can make a graph, because, you know, we pretty much graph everything, in case you haven't figured that one out. And what we plot would be the vertical height on those ripples as a function of distance from the point where the pebble hit. Okay. And then what we're going to find we get kind of a pattern, something like this, okay, where this particular point here is indicated by that point on this graph. This point here is indicated by that point on the graph. And this point here is indicated by that point on the graph. Okay. And so then what you're doing is that these, you know, ripples, these are going to create, you know, all the peaks kind of things. And no matter how we go out, it's the same kind of picture. So there's all the peaks here as they travel outward, and then there's a trough down in here and all the peaks there, another trough here, and then all the peaks there. Okay. And so then what we get is that these concentric circles that represent all the peaks, these are your wave fronts. I guess technically, since we're only in 2 dimensions on the surface of the water of the pond, then these would be circular wave fronts. But that's not quite really where we want to be. And what we want to take a look at, if these were to move in 3 dimensions, like if I were to, you know, snap my fingers like this, then that amplitude of that sound wave would travel out. And as long as the medium in which the sound wave is traveling is isotropic, that means that the speed is the same in every direction, then our wave fronts would not be circular wave fronts, but they would be spherical wave fronts. Okay, so in 3 dimensions, what we get is that these would produce, you know, spherical wave fronts. So outward they go. And so wave fronts, and let me mark that these are, you know, all peaks, like so. And so then let's go in. And one of the things that we want to go in and discuss is that so if we recall that energy in a wave is given in general by the amplitude of the wave. Okay. Okay. And if we go specifically, we can remember that, you know, for simple harmonic motion, so SHM, then the energy of our simple harmonic oscillator, the object that's undergoing simple harmonic motion, is going to be given as, you know, 1/2 K, which was the spring constant, times A, which is our amplitude squared. Okay. And therefore, if we, you know, shape the object in simple harmonic motion like the end of a string, then we're going to generate, you know, harmonic or sinusoidal waves. And so, since this was the energy of the oscillator, then the energy of the oscillator gets transmitted outward by the waves that emanate out from that, you know, shaking the end of the string kind of idea. So then the energy in the wave is going to be proportional to the amplitude squared. Okay. And if we recall, then our amplitudes are essentially, this type of height. This is the amplitude of our wave. And since this is the repeat length versus a position type of idea, then that repeat's going to be what? What quantity is this? Repeat in position. There are two likely answers, one that's not right and one that is right. So I'm trying to make sure we're good with the one that is right. Uh, 2 pi would be the phase change between those 2 points in radians. So, but that's not quite what I want. So like on a math graph, if we plotted that versus angle, then that's what we would get, is it would be the angular distance between the peak to the peak would be 2 pi or 360 degrees. Well, if this was plotted versus time, then the repeat in time is the period. But since this is plotted versus position, then that shortest repeat in position is our wavelength. Lambda. Okay. And like I said, it's really easy to mix up the period and the wavelength. So I was trying to, help out with making sure we keep those straight, because you draw the exact same picture, but with time, and then that would be the period. So you got to be careful with the graphs. They look basically identical. So, all righty. So there's our wavefronts. These are spherical wavefronts. If we're in 3 dimensions, like I said, they'd be, I guess, circular ones if we're in 2D, but we pretty much want to be in the 3-dimensional type of thing. And then what we can look at is we can take a look at our rays. So the waves traveling outward like this. And so we draw a line in that direction, and it crosses these wave fronts at 90 degrees. Then what we would get is that these would generate rays. Now, the thing is that we're going to have an infinity of rays that we can draw. And for the most part, we generally draw the ones that are useful. Okay. And so, they can go all which ways, but these are the rays. Those are the rays, like so. Now, the other thing that we would often talk about is that as these wave fronts travel outward, or as the ripples travel outward, then very often what will happen is that the height of the ripple, which is related to our amplitude in this wave, the height of the ripple will get smaller as they go further out. Okay. So we might start off with a fairly big ripple here, but then the ripple gets smaller here, and then smaller even yet here, like so, as it goes out. And then you're like, well, so these amplitudes would technically be decreasing as they plot further out along the position. And since the energy goes as the amplitude squared, this might lead one to believe that that we've, quote unquote, lost energy, right? Transferred it to other forms or whatever, right? Like really lose energy. So then you might go, well, what happened to the energy? And the answer is that as it goes further and further out, it's getting, diluted over greater and greater, areas. And so this is why back in chapter 12, they talk about the intensity. Okay. And so then we have that our intensity, they use a capital I for that, is going to be the energy being transported by the wave divided by the area. Okay. And if we go and we look at this energy per time, then this is, of course, the rate at which the energy is being transported, with respect to time, is the power. So then what we get is that this is our power over this area. And so what this allows us to do is this allows us to talk about that as this wavefront travels further and further out, then the energy in the wavefront is getting diluted more and more over greater and greater surface areas of those wavefronts. And so then what that implies is that, if this was a sound wave, then the further out you go, the softer it'll get. And if it was a light wave, then the further out we go, the dimmer it will get. And so that describes the fact that the further you move from the source of the wave, then the less intense it becomes. So for a sound wave, that's softer. For a light wave, that's dimmer. Kind of ideas. Okay. And so let me make a couple little notes. And so this will be a useful thing for us, this intensity concept. So hopefully y'all remember some of that. And so one thing that we should also note, and I mentioned this, but let me write it down, is that there's going to be an infinity of rays that can be drawn. But we're only going to draw the ones that are, useful to us in that situation. Okay. Well, you can draw an infinity of rays. We'll only generally draw the ones that are going to be, helpful or useful or whatever kind of things. And so what we'll get is that in geometric or ray optics, we can treat electromagnetic waves as if they are rays. And this will allow us go in and describe, several wave properties. Okay. But not all the wave properties. Predominantly, what we can describe in this manner is we can describe reflection and refraction. Okay. And so you probably have a pretty decent idea of what reflection is. That's, reflecting or bouncing off of surfaces or off of, surfaces where you go from like air into water or air into glass or glass into water kind of things. And when we talk about refraction, then this one has to do with the fact that the light ray will be bent due to a change in wave speed, likely due to the change in the medium. Okay. If you change from one medium to the next, then we've changed the wave speed. And therefore, what will happen is that in general, the direction of the ray will change. And so this is called refraction.